Motion of charge in a magnetic field. The region of the atmosphere existing about 80 kilometers from the Earth's surface is called the Ionosphere. It consists of charged particles and plays a crucial role in long-range radio communication. The ultraviolet rays from the sun ionize the air molecules in this region and produce ions and electrons. Now, let us study why these ions do not escape to outer space. And how do they form the ionosphere? We know that the equation of the magnetic force vector Fb, which acts on the charge Q moving with a velocity vector v in a magnetic field vector B, is vector Fb equals Q into vector v cross vector B. Its magnitude can be written as Fb is equal to QVB sin theta, using the cross product. Here, theta is the angle between the velocity vector v and the magnetic field vector B. This equation tells us that if a charge moves in the magnetic field with its velocity vector v parallel to vector B, that is, theta equals 0 degrees, the magnetic force acting on the charge is 0. The same is true if vector v and vector B are anti-parallel, that is, theta equals 180 degrees. In both the cases, the motion of charge is not influenced by the magnetic field. Consider a freely moving positive charge Q entering the magnetic field, such that vector v is perpendicular to vector B. For this case, theta equals 90 degrees, and hence the magnitude of the magnetic force is maximum and is Fb equals QVB. To find the direction of Fb on the positive charge, we use the right-hand rule. Orient your first finger along the velocity vector v and second finger along the magnetic field vector B. The direction of the thumb gives the direction of the magnetic force Fb. This force changes the path of the charge in the magnetic field. At point L, the force Fb is perpendicular to V. This force bends the trajectory of the charge and it reaches M. At this point, the force pulls the charge inward, bending its path further, and the charge reaches the point N. The charge is acted upon by a constant centripetal magnetic force at every point of its trajectory. As the force is always perpendicular to its velocity and hence the displacement, the work done by the magnetic force on the charge is 0. The energy of the charge remains constant and hence its speed also remains constant. Therefore, the magnetic force merely changes the direction of the velocity of charge and not its magnitude. As a result, the charge performs a circular motion within the field. Since the charge is now held, we say that the magnetic field can trap the charged particles. The above fact is true for the negative charge also, but the direction of the magnetic force acting on it is opposite to that given by the thumb in the right-hand rule. For circular motion, the centripetal force F is equal to mv squared over r. Here, the centripetal force is provided by the magnetic force Fb. Hence, QVB is equal to mv squared over r. Therefore, the radius r of its circular orbit is r is equal to mv over qb. The experimental demonstration can be seen using a device called a fine beam tube. This is a vertically oriented spherical chamber containing an inert gas at a low pressure. There is an electron gun mounted horizontally inside it. Two coils called Helmholtz coils, arranged as shown, produce a uniform magnetic field perpendicular to the axis of the electron gun when the current is passed through them. When the electron gun is switched on, one can see a bright ring inside the bulb. At a microscopic level, one can see that this is due to the presence of the magnetic field B. The magnetic force Fb forces the electrons into a circular motion as explained earlier. During their passage, the electrons interact with atomic electrons of gas and excite them, which in turn de-excite and emit radiation. A large number of such interactions along the circular path individually emit radiation that can be collectively seen as light in the form of a ring at the macroscopic level. Increasing the accelerating potential increases the speed of the electrons. As a result, the radius of the ring increases. Increasing the current in the coils results in an increase in the magnetic field. Consequently, the radius of the circular path decreases. These observations are in accordance with the derived formula. Let us consider the case of a cathode ray tube, CRT. When no potential is applied to its deflecting systems, you can see a spot at the center of its screen as the electron beam strikes the fluorescent screen. If you place two bar magnets facing their opposite poles, as shown, the point is deflected. This is because each electron is influenced by the magnetic force due to the magnetic field and is deflected from its straight path. In a CRT, the bar magnets produce a weak magnetic field and the electrons have a very high velocity. Hence, the radius of curvature of the electrons is very large compared to the cross-section of the magnets. Consequently, the path traversed by electrons in the field is a circular arc of radius r. The electrons don't get trapped and can escape the field. They move further along the straight line to strike the screen and form a spot. Now, fire a positive charge with its velocity vector, making an angle theta with the magnetic field. The vector v can be decomposed into two perpendicular vector components. One is parallel to vector b. Vector v parallel equals v cosine theta I cap. The other is perpendicular to vector b. Vector v perpendicular equals v sine theta j cap. Since the angle between vector v parallel and vector b is 0, the parallel velocity component is not influenced by the magnetic force and contributes to its linear motion along vector b. However, the component v perpendicular, being perpendicular to the magnetic field, is subject to a magnetic force causing circular motion of the charge in the plane perpendicular to vector b. Hence, the motion of charge is the resultant of the linear and circular motion, which is a helical motion with a definite pitch. As the angle theta between velocity and magnetic field increases, the pitch of its helical path decreases. The pitch is given by the formula 2 pi r v parallel over v perpendicular. For its experimental proof, rotate the electron gun of the fine beam tube. You can see that the ring takes the form of a helix. This implies that the trajectory of the electrons is helical inside the bulb. Let us now consider the question we first posed about the ionosphere. We know that the Earth has its own magnetic field. When air particles are ionized, ions and electrons are produced. And the Earth's magnetic field does not let them escape from the atmosphere and traps them as explained earlier. The motion of positive and negative charges is opposite in direction, and the charges follow a helical path around the magnetic field lines. This is how the ionosphere is formed. Now, can you guess why the picture of a conventional television becomes distorted when a magnet is kept near it? Summary. The magnetic force vector Fb acting on a charge q moving with a velocity vector v in a magnetic field vector b is vector Fb equals q into vector v cross vector b. For the cases when theta equals 0 degrees and theta equals 180 degrees, the magnetic force acting on the charge is 0. For the case theta equals 90 degrees, the magnetic force is maximum. Under the influence of this force, the charge performs a circular motion within the magnetic field. The radius of the circular orbit is given by r equals mv over qb.